Hi, I'm GUO CHENG GUANG, 12 years old, Primary 6 from YUMIN Primary School. For the examples in this lesson, we are going to use two different methods. So in this example that we have right now over here, the first method is by induction. The second method is the method that we have learned before. You change from limit calculation into definite integral. So let me just write down this example on this board. So this example is limit n approaches to infinity. Then you have 1 square plus 2 square plus 3 square plus all the way until n square. Then the denominator is n cubed. Now let's use our first method by induction. So method 1. We can call it proof by induction. Now proving by induction, at the numerator, let's take a look first. So we have 1 square plus 2 square plus 3 square plus all the way until n square. Now what kind of formula we use to find this sum? So for this is the 1 over 6 then times n. Okay. Then after that is n plus 1 and 2n plus 1. Now this is the formula that we use to find the sum. First, let's check whether we got this right. So we can use one number to check. For example, n is equal to 1. Then this 1 square is still a 1. It would be equal to, so 1 over 6 times 1. 1, you just don't need to write. Then n plus 1 is a 2. 2n plus 1 is a 3. So it is still equal to 1. So this you can first say is sort of correct. But let's try. Now what if we let n be equal to k? So this would become 1 square plus 2 square plus 3 square plus all the way until k square. And this would be equal to, now just changing this n for a k. So 1 over 6 times k, then bracket k plus 1, then 2k plus 1. So this is when when n is equal to k. But what if n is equal to k plus 1? So 1 square plus 2 square plus 3 square all the way until k square. Then another term, k plus 1 square. But what if we just write this down first? We don't straight away write it down into what the formula should be. We use the original one all the way until k square. So it is the 1 over 6k times k plus 1, 2k plus 1. Then because there's this additional term, so you also need to add it on the other side. Now, in order to make sure that this formula is correct and we can use it, we have to make sure that when we simplify it to the simplest, we actually can relate it back to this. When we relate it back to this, it is similar. That means using the same formula. So what can we have first? Now, at first, you might think of factorization. And yes, we should use factorization. We have a k plus 1 that we can factorize. Now to make this simple, we take this fraction out. That is the 1 over 6. So then inside here, what you have is k times 2k plus 1, this part, then plus k plus 1. But wait, because you took out 1 over 6, so that k plus 1 needs to times 6. So it becomes 6k plus 6. Then from this, 1 over 6k plus 1, we just let it be the same at first. Then inside here, we'll try to simplify it. Okay, maybe we could expand this part first. So that means inside would be 2k squared plus 7k plus 6. Now, we just need to factorize this part. Well, how can we factorize? Well, simple. We can use cross multiplication. So 2, well, it just comes from a 2 and a 1. 6, well, we can say comes from a 2 and a 3. This 1 and 2, 2 and 3, just 1 times 3 and 2 times 2. And that makes up this 7. So this one is with a 2. And this 2 is a 3. Now in this part, to make sure that it's something like this, we'll need to, like, if this is plus 1, then we plus 1. For this part, then plus 1 again. So this is actually still the same. Then for this part at the back, 2k plus 3. Well, of course, at first is k plus 1. Now we need 2 of the k. So you have 2 of them. But you'll still need this 3, but you only have a 2. So plus 1. Now, is this right? So first, wait. This part is not k. This is k plus 1. Okay, like this. Now, this is much better. 1 over 6 is still the same. Then n is k plus 1. Yes. Okay, so they're all right. And what does that mean? So we can make a conclusion. This, well, we can call it a statement. This statement, well, we can say that it is correct, right? So we can say that this statement is correct. And when we say that this is correct, can we just sub it inside here? So let me just write it over here. Now this limit n approaches to infinity. Okay, this thing, just write it down here. 1 squared plus 2 squared plus 3 squared plus all the way until, wait, this is not t, plus n squared. Then you have to over n cubed. So this, it would be equal to, on the numerator, we apply this formula. So it will become limit n approaches to infinity, 1 over 6. Well, that one we also use n, so same thing. Now, you'll find one thing. 1 over 6, you can take it in front first. Then inside this limit, perfectly we have 3 of the n. So n times n times n, right? Now we give 1 n into each of these. So n over n, 1. N plus 1 over n, so 1 plus 1 over n. Or we can say it as like that. and then behind is 2 plus 1 over n. Now, 1 over n, they all become 0. So inside here is only a 2. So 1 over 6 times 2 is a 1 over 3. So 1 over 3 should be your answer. And this is method 1. Okay, so this is method 1. Next, we'll move on with method number 2. So this answer is 1/3. Okay, so can I erase this part, this method 1? Okay. So we're just recording down this answer. Okay, next, method 2. Well, method 2 is what we have learned for the past few lessons. And from these past few lessons, we have been learning about, we change the limit calculation into the definite integral. Now changing this. So what can we change it into? Or maybe I just write this down first. Now, you realize the pattern here. All of these in the numerator is a square. Now, and they're also all adding together. So, when you realize that, let's write this first. Limit n approaches to infinity. 1 over n cubed. Well, it's got nothing to do with the next part. Because this square, now this sigma, what can you think of? Well, maybe you just let another be I. So it starts from a 1. And inside here is the I square. Now this is all the way until n. Like this. So from this, but it might look better if we actually put this 1 over n cubed in. So let me just write that in. Now this over n squared times 1 over n. So like this. Well, at this part, this I squared over n squared, we can make a substitution so that we could change this into a definite integral, and the part behind the 1 over n, which approaches to 0, we'll just make it as dx. So for this, we'll let I over n be xi. And then delta x, it would be, okay, we can just say it as x I plus 1 minus x I. And this is 1 over n. So then we're very sure that this part is the dx later on in the definite integral. Then we'll have to find, for a definite integral, what is its boundary. So 1 inside here, 1 over infinity, we can just write it as 0. Then n over n, it will be a 1. So the boundary is from 0 to 1. 0 to 1. Then inside here is actually x squared, then dx. And then integrate this, so it's a 1/3 x cubed. Then you have to sub 0 to 1. And so what you get at last is a 1/3, like this. So the answer is the same, so that means this method is correct. Okay, so what types of methods have we used? So first from this is actually you change this from writing it as in our normal way, everything plus together, you write it into the sigma notation. Then after that is to change it into definite integral and then solve it and sub in. Well, for induction method, it's a little bit different. When you just look at that numerator, but for some questions it might be the denominator because they can reciprocate. So when it becomes like that, it's actually you first know it's a formula, then you prove that this is actually right, and then you can use it. So for this lesson, I will end here. So if you like our videos, don't forget to subscribe to our channel. So we'll see you in the next lesson. And thank you for your watching.